What do an ancient Greek philosopher and a 19th century Quaker have in common with Nobel Prize-winning scientists? Although they are separated over 2,400 years of history, each of them contributed to answering the eternal question: what is stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space. And he even speculated that they vary in size and shape depending on the substance they compose. He called these particles atomos, Greek for indivisible. His ideas were opposed by the more popular philosophers of his day. Aristotle, for instance, disagreed completely, stating instead that matter was made of 4 elements: earth, wind, water, and fire. And most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments had shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom. The idea that electrons cannot be pinpointed but exist within a range of possible locations gave rise to the current quantum model of the atom, a fascinating theory with a whole new set of complexities whose implications have yet to be fully grasped. Even though our understanding of atoms keeps changing, the basic fact of atoms remains. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelengths of light, resulting in all the marvelous colors we see. And we can imagine Democritus watching from somewhere, satisfied that over 2 millennia later, he turned out to have been right all along.
All right, so you just watched the video on the atomic theory, and it talked about how that theory has changed over time as different pieces of evidence came up. The discovery of the electron led to a new model of the atom. The discovery of the nucleus led to a new model of the atom. The discovery of different energies in electrons and the discovery of the neutron have all led to different models of the atom. So as new evidence comes up, the theory changes. A scientific theory is an explanation of why something happens. It's a tested explanation, and it gets proven over and over again. And all it takes is one observation that makes a theory untrue, and all of a sudden the theory either needs to adapt or it becomes obsolete. In the case of some obsolete theories, there was a theory of spontaneous generation. Doctors used to think that diseases spontaneously grew inside of people. They didn't know about germs at the time. So whenever the discovery of the germ came about, all of a sudden that theory had to be revised or rejected. In this case, it was rejected because there is no spontaneous generation of organisms. So a theory is an explanation for why something happens. In the case of the theory of evolution, it's an explanation for how organisms change and adapt over time, how they mutate genetically and or change their behavior so that they can respond to changes in their environment, whether it gets too cold or the food source goes away or the water dries up or the environment, the plants change. Whatever happens, something in the environment causes the organisms to change. If they don't change, they go extinct. So in the case of the theory of evolution, the theory of evolution is much like a scientific theory. If an explanation comes up that doesn't fit with the theory either needs to change and adapt, like the animals, or the theory is killed. It's deleted, like the theory of spontaneous generation. A law is an explanation of how something works. It doesn't give you the why, it just says how something works. In the case of Newton's laws of motion explain how moving objects interact with each other. They explain that an object, it resists changes in motion. If an object bumps into another object, it responds with an equal and opposite reaction, and you can calculate the amount of force necessary to change the acceleration of an object by using the formula that Newton came up with. So he gave lots of explanations for how things happen, but he doesn't explain why. He didn't get into the details of why inertia exists or why it takes that amount of force. He just explained the why. Speaking of Newton, Newton also came up with a law of gravity. In his law of gravity, he explained that it's the mass of two interacting objects as well as the distance between them that determines the force of gravity. The larger the object, the more gravity it's going to have. The further the distance between the two objects, the weaker the gravity is going to get. If you were to travel from the Earth out to where Neptune is, the sun would have a weaker force of gravity on you because you'd be further away from the sun. So the further away you get from the object exerting a gravitational influence on you, the weaker that gravity gets. In order to explain the how it happens, or the why, in order to explain the why it happens, you need a theory. So in the case of Newton's law of gravity didn't explain why gravity works. In order to determine that took another couple hundred years. An unknown scientist, who wasn't really a scientist at the time, he was a patent clerk, wrote a paper that said, I think I figured out why gravity works, and Newton was wrong in some instances. And a lot of people took offense to that because Newton had been accepted as a genius in the scientific community for generations, for hundreds of years. People agreed with Newton, and then here's this little guy comes along and he says, no, Newton might be wrong. He's partially right, but he's also partially wrong. When he published that paper, a lot of people realized that he was correct, and they accepted Einstein's theory of gravity. Einstein explained that large objects are bending space, and it's that bending of space that is causing a gravitational field. The larger something is, the more space is bent. So imagine being on a trampoline, and in the middle of the trampoline is a small 3-year-old boy. The 3-year-old boy isn't going to push down on the trampoline much, so if you rolled a ball across the trampoline, it probably wouldn't fall towards the boy due to the curvature. But if you put a car in the middle of that trampoline and you could keep it from popping the trampoline, then that car would bend the trampoline so much that when you tried to push the ball across the trampoline, it would go down into the car and bang against the car. So the car represents something that's very massive. The 3-year-old boy represents something that's not very massive. So that's Newton's explanation for why gravity works. The Big Bang Theory. Evidence has shown over and over again through redshifting of distant galaxies that are moving away, through background radiation, through other observations that we've made, that the universe started as a single point that exploded about 14.5 billion years in the past and has been expanding ever since, which is why everything is moving away. As things get further away, they get cooler, they emit radiation from the initial explosion, and the redshifting is an indication that distant things are moving away. So there is evidence to support the Big Bang Theory. But like all theories, all it would take is a single explanation that does not align with the current understanding of how the Big Bang Theory worked to make that either change or to scrap it and delete it altogether. Same thing with Einstein's theory of gravity. It's not a perfect theory. It explains the very large, but it kind of falls apart whenever you start to talk about the very small. Whenever you get down to quantum mechanics, like atoms and quarks and string, it doesn't fully explain how small objects, very tiny objects, exert gravitational forces on each other. All right? So the difference between a law and a theory: a law explains how a natural phenomenon happens. A theory explains why it happens. It gets into the underling and it says this is why that happens. All right? The force of gravity is a pulling force. Objects are pulled towards other objects due to their mass. So the larger their mass, the more the force pulls. Moons tend to pull with less force than planets because planets are always more massive. Stars pull with more force than planets because stars are much more massive than planets. In the Earth-Sun system, the Earth is being pulled by the gravity of the Sun, but the Sun is also being pulled by the gravity of the Earth. Because the Earth is so tiny in comparison, the effect on the Sun is so much smaller. The reason we don't fall towards the Sun is because the Earth also has forward velocity. That forward velocity combines with the inward pull of gravity to give the Earth a circular-shaped orbit. Now, all objects fall towards the Earth at the same rate when you ignore air resistance. For extremely light objects, though, like feathers, the air pushes back with a force that counteracts gravity a little bit. It causes the object to fall slower than a heavy object. That's why feathers fall to the ground slower. If you sucked all the air out of the room, the feather would fall at the same rate as the heavier object. So you would need to ignore air resistance. Lastly, the same thing happens with the Earth-Moon system as with the Sun-Earth system. The Earth is being pulled by the Moon, but because the Moon is much less massive, the effect isn't as noticeable. One noticeable feature of the Moon's gravity is tides on the planet. Ocean water on our planet is being pulled towards the Moon and also the Sun, and that's what makes tides. So 2 times a day, we have ocean levels that rise in a single location, and 2 times a day, those ocean levels fall. And this is due to the Earth rotating or spinning on its axis and being closer or further away to the Moon when you're talking about a single point on the Earth. Now, the Moon is also being pulled towards the Earth, but its forward velocity is giving it a circular orbit too, which is why it doesn't crash into the Earth, just like we don't crash into the Sun. All right, now let's do amplitude. I want you to do 1 block to 1 block. No, go faster, make some waves. That's 1 block to 1 block. What do you feel? Alexandra, what do you feel? You feel it strong. All right. Chase, same speed, 2 blocks to 2 blocks.
No, I What do you feel? That's much stronger, much more power. Okay, Chase. All right. Chase, can you make a transverse wave? All right. So that is a low frequency going from one block to one block wave. All right, stop. Alexandra, can you make a high frequency wave as fast as you can? So the waves are getting shorter, and there are a lot more of them in there. Frequency is a measure of how many waves pass a given point each second. These waves are moving faster, they're smaller, and they're hitting faster. All right, that's frequency.
All right, so for the second part of Station 15, what it's asking you to do is, it gives you an original wave. And this is a drawing, it's not perfect, but it's a drawing of the wave that is at the top of your paper, this wave right here. For card 1, it tells you that it wants you to change some feature of that wave. So for our wave, I want you to double the amplitude. Now, if you remember from the video you just watched, you know that the amplitude is the height of the wave. In my example, I'm using an index card. The wave goes 4 lines up and 4 lines down. In order to double that, I have to go 8 lines up and 8 lines down. But it's only asking me to double the amplitude, and which means that I have to keep the frequency the same. I have to have 4 peaks on top and 4 dips on the bottom. So I'm going to try and draw this as easily as I can. Up, down, up. See, it's not perfect, but down, up, down, up, down, and back. So it's the exact same wave. It's got the same frequency. 4 waves at the top, 4 waves at the bottom. It crosses 4 different times. The only difference is that in this case, it is double the amplitude. It is twice as high as the original wave. For card 2, I'm asking you to increase the frequency. So in this case, there are 4 waves. In order to make it faster, I need to make more waves. So I'm going to try and make 8 waves. So let me see if I can do this. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20. All right, I'm going to stop there because I've got 10 and 10. You can see how the height of the wave is exactly the same. The waves are just smaller, the wavelength is smaller, and there are more of them packed in the same space. So that is increased frequency. When you increase the height, that's the amplitude. When you increase the number of waves, that's the frequency. All right? For card 3, I want you to increase the wavelength. I want you to make the waves longer. So just like the previous one where we made the wave shorter and we increased the frequency, now we're doing the opposite. We're going to make the waves longer and we're going to decrease the frequency. So we're looking for longer, slower waves that pass through the same points. So let me do a nice long, slow. That is half of what this is, because there are 2 peaks and 2 valleys. There are 4 peaks and 4 valleys, troughs, not valleys. And so this wave is half of the frequency of this wave, and this wave has twice as long in the wavelength department as this wave does. So when you're drawing waves with longer wavelengths, you lengthen the frequency, or sorry, you shorten the frequency. The frequency in this case is 2. The frequency in this case is 4. You shorten the frequency and you make the wavelengths longer. So here's where one wave starts and there's the other wave. So that distance there is one wave. In contrast, this distance here is one wave. So you can see how the wave is twice as long, which is why there's only half of them packed into that same space. In this case, the frequency is 10, because I've got 10 waves. 10 peaks and 10 troughs in there, all packed in the same space. So when you change the frequency, you change the number of waves, you also change the length of the wave. Increase the frequency, the waves get smaller. Decrease the frequency, the waves get longer. The last one, I want you to decrease the energy. Remember, the energy is related to the height of the wave. When we made our waves nice and big, when we made the amplitude higher, we added more energy. Remember what Alexandra said in the video. When Chase made the slinky higher, she said she felt more energy. So that's this. When you make those waves lower, you keep the same number of waves, but you decrease the height of the waves. So these waves are half as high as these waves. These waves are twice as high, which means that these are going to be more energy, these are going to be less energy, these are going to be the lowest energy. All right, so that's station 15.